All right, so we're going to jump into some new reactions with alkynes. A lot of these look remarkably similar to the reactions we've seen with alkenes, which is kind of handy. All right, so let's recall hydrohalogenation with alkenes. Oh my goodness, my brain is not working. All right, if we have an alkene and we react this with HBr without peroxides, will we get Markovnikov or anti-Markovnikov addition? Markovnikov. All right. So bromine will attach into the more substituted carbon. The hydrogen will go on the less substituted carbon. Pretty simple. Do we need to worry about enantiomers? No, this is an achiral compound, so we don't need to worry about it. All right, so this led to an original hypothesis with alkynes. Oops. So originally they had the idea of taking a simple alkyne. We'll just make up one like this. You react it with HBr. If that happens, one of these pi bonds could steal a proton from HBr, kick off bromide. We would then have a carbocation on the more substituted carbon. Let me make this a straighter line, just like we saw last chapter. And then bromide, as our leaving group, one could hypothesize that this bromide ion would attack back into that carbocation. And you would get this final product. There's one interesting thing with this, though. They did this reaction, and they were able to isolate this final product. But the problem was they weren't able to find any evidence of the intermediate. So let's make a note of this. This is called a vinylic carbocation. So they were kind of stumped. They knew that they were making the final product as shown, but they couldn't find any evidence that it went through this intermediate in any way, shape, or form. So what they decided to do after that was to do a bunch of rate experiments. And if you remember from SN1 and SN2, you can learn a lot about a reaction's mechanism from the rate equation. And so the rate for this equation was found to be a rate constant times the concentration of your alkyne times the concentration of HBr squared. So then it kind of complicates things. So when you double the concentration of HBr, what would that do to the rate? It would quadruple it, which doesn't make a whole lot of sense. If we look at the above mechanism as shown, it's not going to quadruple if you quadruple HBr's concentration, right? So what they had to do is come up with a better hypothesis. And even this one's kind of debated still. It's the best answer we have to this problem. And I'm going to show it by labeling all of our specific carbons and hydrogens. And what they think happens is that one equivalent of HBr is underneath, another equivalent of HBr is on top, and that this bromine will actually attack into this carbon, and that this pi bond will attack the hydrogen in a concerted step and eject off bromide all in one go. The transition state for this is pretty crazy. You're breaking one of these pi bonds, so you could show it as a dash. You're making a bond to the proton on the top HBr. You're breaking a bond to this bromine. You're making a bond to this bromine, and then you're breaking a bond to its hydrogen. So this would be the transition state. This is called a termolecular transition state, basically meaning that it involves the collision of 3 different reagents in order for the reaction to proceed. It explains, at least in theory, why the HBr is second order, and the alkyne is first order for this reaction. This is our best theory. It still kind of looks funny in my opinion, but it is the best thing we have to explain the overall outcome for this reaction. So when all is said and done, we make a new alkene, and the bromine in this case is always going to favor the more substituted side of the alkene, and then your byproduct for this reaction is going to be HBr. So it's not only a reagent, but it's a byproduct. The nice thing with this mechanism is it avoids that vinylic carbocation, which is incredibly unstable, and we don't have any evidence that the carbocation exists in this mechanism. Oftentimes students will ask me, how do we know that this is the true mechanism? The reality is we don't. We, as chemists, when we try to elucidate a reactions mechanism, we can prove a mechanism wrong, but we can never prove it right. We can just have a lot of evidence saying, well, it's most likely going to be this because we've ruled everything else out as wrong. That's essentially how we get there. What? Yep, that's exactly how most of science works. It's just the most plausible explanation we have at a given point in time. All right, so let's take a look at this in practice. So let's say I've got this aromatic alkyne, and I react this with HBr. We can either have HBr attack at that red position or at the green position. Where's the bromine going to be installed? The red one, right? So just like before, favors Markovnikov, goes through that funky transition state. We can get to our monohalogenated product. What happens, do you think, if we react this with more HBr? It would continue, right? Would it add at the red carbon or the green carbon? The red one. All right. So we would have 3 hydrogens out here. We would have 2 bromines coming off of the more substituted position. What's this type of halogen called? Does anybody remember from yesterday? It's a geminal dihalide. All right. My question for you is, what if we want to go backwards, back to our starting material? You know, just for fun. What do you guys do for fun? This is what I do. Yeah, super strong base, that sodium amide. And you're correct. Why do we need water as a second step for this reaction? It's a terminal alkyne. We have to reprotonate that proton coming off the very end. So you can react this with water at the very end. So often with these reactions, you can interconvert between alkynes and alkenes, as you saw with your problem of the day, and you can accomplish a huge number of functional group transformations by doing that. All right. So now the question is, can we get a bromine to install off of the less substituted carbon? The answer is yes. What do you think we need to do in order to accomplish that? Peroxides. All right, so anti-Markovnikov halogenation, like we saw with alkenes, can be accomplished using peroxide. Like I said, the peroxides that are normally used are going to be alkyl peroxides, so we normally abbreviate those alkyl groups with R's. It doesn't really matter which alkyl group they are. And when you do this, you'll get the bromine to install in the less substituted position. With alkynes, we're not going to really get into the mechanism because it involves a radical mechanism, and we haven't learned about radicals yet, but the same idea is true. However, we have to be more careful with this one because we can run into different isomers. Is this the E isomer or the Z isomer? It's an E. It's an E alkene that you might get with the halogen, or you might get the Z alkene. Will these be very easy to separate and purify? Yeah, what's the relationship between them? Yeah, they're diastereomers. Diastereomers have different physical properties, so we could separate these using a variety of separation techniques. Like I said, we'll go back to these reactions a bit more when we cover radical chemistry, but don't worry about the mechanism for right now. Make sense? All right. The next one is also closely related to the reactions we saw with alkenes. This is acid catalyzed hydration. Yeah. Yeah.
Oh, never mind.
Okay. Question solved. Yeah.
So if the HBr was in excess, could it?
Yes, it could. So the question was, if you have it in excess, you could potentially overshoot and make a halogenated alkane, so a geminal dihalide as well. Yeah.
So and it would it be general or would it go to other, like, or would it be a mixture of it?
So you would, if you overshot this one, I'm pretty positive this would be kind of a weird reaction, but you would get a geminal dihalide with both halogens coming off the less substituted carbon. Does that make sense?
Yeah.
Because it would still be anti-Markovnikov. You want to form your... Actually, let me think about that. I'm pretty sure, yeah. Well, it's not a super common reaction, but I'm like 90% sure that's what would occur. Yeah. All right, so acid catalyzed hydration. If you remember with alkenes, we needed catalytic acid. Normally that's sulfuric acid. You could use phosphoric acid. You could even use an organic acid like tosylic acid if you want. And water. And just like with hydrohalogenation, your alcohol will go to the Markovnikov position. So then that led to the question, can we do the same thing with alkynes? The answer is kinda. All right. So if you take this and you react it with acid and water, you get no reaction. The activation energy is too high. What is a possible workaround when you have a super duper high activation energy? Add a catalyst. So trick, use a catalyst. And I remember when I took organic chemistry at first, I always thought that there was some sort of super logical explanation as to why one catalyst was chosen over another. The reality for a lot of these was that in the early 1900s, they just screened literally tens of thousands of different things, and they found one that worked better than the others, and they went, I'm not going to ask why, it works. So in this case, the catalyst that works is a mercury 2 catalyst, which is kind of unfortunate because mercury is not the greenest reagent. But I'm going to show all of our carbons in this, and you'll see why in a second. But you still need the acid and water. Normally the acid is sulfuric acid. And you need mercury 2. However, often what you'll see in the book is mercury 2 sulfate as the catalyst. And when you do this, you're still going to get Markovnikov hydration, right? Which means that your alcohol is going to come off the more substituted carbon, and your hydrogen is going to come off the less substituted carbon, and your intermediate would look like this, right? This is called an enol. Does anybody know why this is called an enol? What functional groups does this have in it? It's half alkene, half alcohol. Therefore, we call it an enol. Right? Pretty clever. All right. All right, so the next step in this reaction is you still have your acid around, right? So I'm just going to write our hydronium ion that's floating around in solution. We know that alkenes can react with acids, okay? So this alkene can grab this proton from our acid, and then the question is, where is the positive charge going to end up? So I'll let you think about what the likely intermediate is going to be. I'm just going to draw my skeleton structure for right now. In fact, let's compare these. I'm going to zoom out. All right, which intermediate do you think is more likely, the one on the left or the one on the right? Oops, I forgot my hydrogen here. Why is the one on the left more likely? More substituted? Is that the main reason? What's more powerful than hyperconjugation? Resonance. If we think about the one on the left, it has resonance stabilization and it's more substituted, right? So we could cross this one out and we could say that's not likely to occur. However, we've got lone pairs on this oxygen. That can dump down. We can redistribute that positive charge across two different atoms. I'll go ahead and draw all these hydrogens in. All right, to show that these are resonance structures, don't forget your double-headed arrow and brackets to indicate that these are a hybrid of one another. Which structure do you think is the major contributor? The resonance structure on the left or the resonance structure on the right, and why? The left one, but oxygen doesn't like a positive charge. Well, I heard somebody say it. What's the number one thing we look for with major contributors for resonance structures? Full octets, right? If we think about this structure on the right-hand side, this carbon doesn't have a full octet, so that's going to be a minor contributor, but it's still there. So I'll just write minor and major. This has full octets. So the structure on the left is a more accurate representation of what's actually existing in solution. We still have water floating around. We don't like having a charged intermediate, so what do you think the last step is going to be? Deprotonation. So water can grab this proton, dump electrons onto that oxygen. And we regenerate our acid, which tells you what about our acid in this reaction? It's catalytic. So the acid and the mercury too are both catalytic. The water in this case is the only stoichiometric reagent that we're using. All right, what's this new functional group that we made? Ketone. All right, so if you noticed in this whole reaction mechanism, besides the first step, I used equilibrium arrows between the enol and the ketone. So it is truly under equilibrium conditions. However, the ketone is highly favored over the enol. So at equilibrium, it's usually over 90% ketone, less than 10% enol. However, you do have a true mixture of them going on in solution. So you can do this reaction back and forth if you'd like. So let's go ahead and say the ketone is the preferred product. All right, this is a reaction we're actually going to see a lot third term, but they introduced it this term already. This is called the keto-enol tautomerization. Specifically, it's an acid catalyzed keto-enol tautomerization. Yes, kind of. Yeah, it is one. Does anybody know what a tautomerization is? This? So if we look at this, sorry, I'm going backwards a bit. I'll zoom out. Between the enol and the ketone, have we changed the molecular formula at all? No, we just shuffled hydrogens around. So a tautomerization reaction is a reaction in which you're just moving hydrogens around, but not changing the molecular formula. So this is a good example of a tautomerization reaction. Okay, so let's make a note that the ketone is favored at equilibrium. And it's usually greater than 90% ketone, but some enol still is present. Does that make sense? So now we have a couple different ways to make ketones. We can make ketones by doing acid catalyzed hydration of alkynes. What's the other way we have for making a ketone synthetically? Anybody remember? Ozonolysis, right? So now we have two different ways of making a novel ketone depending on what functional group we're starting with. And we can even interconvert between alkenes and alkynes as needed. So we're adding more tools to our toolbox. All right. So let's do a little bit of practice. So practice 3,3-dimethyl 1-butyne is treated with dilute acid and mercury 2 sulfate. What is the product? And then show the tautomerization. All right, so I'll give you a minute to work on this one and then check with your neighbor and see if you agree. But this is converting between names to structures and then predicting what the product will be and the final tautomerization. All right, while you're working on that, I'm going to draw the starting material. So we've got an alkyne that looks like this. Oftentimes, to avoid confusion, I'll even show the terminal proton coming off. The one thing to be careful of is if you don't show that, what does that look like? It looks like a new methyl group there. So either have it completely flush like that, or show it with your proton coming off. All right, we've got acid, and we've got water, and we've got our mercury 2 salt, so mercury 2 sulfate. If you remember, I like color coding, so we've got this red carbon, we've got the green carbon. Which side's going to get hydrated preferentially? The red one? Okay, so now we've got our enol. All right, we still have acid floating around. So in our next step, we can show the alkene grabbing the proton from the acid. We want to form our more stable carbocation. And like I said, this is way more stable in this position, not only because it's got more substitution, but because of resonance. So you can show one of these lone pairs dumping down. Now we've got an oxygen carbon double bond. That oxygen now is sharing that partial positive. We still have water floating around too. And what's our last step going to be? Yeah, just deprotonation. And I'll just abbreviate this as CH3. Sorry, it's kind of messy. And we regenerate our acid. I didn't show this with equilibrium arrows. You could have, if you show it with one-way arrows, I'm perfectly fine with that because it's 90% plus going to the ketone form. Does that make sense? Yeah.
So when we're doing this, you have to show that resonance intermediate.
I really like doing that. It reinforces the concept of what resonance is and why that carbocation is more favorable. Yeah.
And then can we show just the blended form?
The hybrid?
Yeah, the hybrid.
You could show the hybrid. However, I normally recommend that students draw all the resonance structures. We'll use resonance a lot, especially when we get into future reactions.
Thank you.
All right. I've got one more reaction. Actually, two more. All right, in this next example, I'm going to have an internal alkyne. Looks like this. We're not going to do the full mechanism for this. We're just going to try to predict the products. And one side of the alkyne, I'll color code as red. The other side, I'll color code as green. Which side is going to get hydrated? The answer is yes, right? One side's not more substituted over the other. There's no preference for hydration, which means we would just get one product, right? Both carbons are identical, they're symmetric, meaning they're mirror images of one another. So let's try to predict the product that we would get for this reaction. And I'm still going to color code it. We would still have this red carbon here. We would have a green carbon here. But now we would have a ketone coming off of what used to be that red carbon. If we had a ketone coming off of the green carbon instead, it would still be the same compound, right? So it's just rotated slightly differently. So the key thing to remember is that symmetric alkynes give one product. All right, you can probably tell where this is going. Yeah.
Do you mean symmetric if they have the same thing on each side?
Yeah, so
Like it's just internal?
symmetric means if we cut that in half, one side is the same as the other side, right?
But it wouldn't be the same if, like, instead of the other ring, you had just a bunch of rings of carbon.
Yeah, if we, let's say, change this ring out to something else, it would no longer be symmetric and we might get more than one product, which leads me into my next problem. All right. Let's take another alkyne that's not symmetric. So this one's got a methyl group on one side and ethyl group on the other. Let's try to predict what products we would get from acid catalyzed hydration. So just like before, I'm going to color code. I've got red and I've got green. Which side do you think is more substituted, the red carbon or the green carbon? I'd say they're both equally substituted, right? They're both bonded to the same number of carbons. So I'd say they're equally substituted, which means they're both likely to occur. So we might have one right? So we've got this red carbon, got the green carbon. We may have one where the carbonyl is coming off that red carbon, and then we might have a second where it's coming off the other position. So this would give you a mixture of two different products. What's the relationship between these two different products? They're constitutional isomers, so radically different properties, easy to separate. So if you have an unsymmetric alkyne, you get two different products. That's pretty hard to tell. Oftentimes there's other things going on, so these may not be a perfect 50-50 mixture. Yeah. Does that make sense? All right. Before we leave, though, I've got one more reaction. We're not going to get into the mechanism of this, but it's hydroboration oxidation, right? And if you remember with alkenes, we said you could react this with BH3 THF, that's the hydroboration step, followed by sodium hydroxide and hydrogen peroxide to give you an anti-Markovnikov alcohol where your alcohol is now off of your less substituted carbon. With alkynes, you can do something similar. However, we can't use borane anymore. So I'll show you a quick example with an alkyne. Oh, that looks messy. In the first one, we're still going to use a boron compound, or boron-containing compound, excuse me, but it's normally R2BH, followed by sodium hydroxide, whoops, I forgot peroxide there, and hydrogen peroxide. All right, just like before, we've got the more substituted side, and we've got the less substituted side. Which side's going to be favored, the red or green? Green. The green, right? So we can go ahead and we can say we're going to hydrate that less substituted carbon, meaning the green carbon. What does this look like? It's an alkene and an alcohol. It's an enol. Ta-da! All right, with an enol, this will really, really quickly tautomerize, and we'll go over this mechanism, I think, next week. But what will end up happening is you'll move protons around, and then you'll get a double bond to form rather than a carbon-oxygen single bond. This isn't a ketone anymore. What's this? It's an aldehyde. All right, the reason we can't use borane, BH3, is that BH3 is too reactive for an alkyne. An alkyne has multiple different types of pi bonds that can react with it, and so it basically runs away from you. You just can't control it. So what we have to do to control it is we have to bulk it up a bit more. That's what the R2 group is for. We need to use a bulky boron-containing compound. All right, so let's take a look at some examples of these bulked up reagents. This is diisoamyl borane. As you can probably tell, that's pretty bulky. One of these can dock with one of the available pi bonds on an alkyne, but two of them physically can't attach to an alkyne at the same time. So you're slowing down the reaction. You're able to control it a lot more. So that's one common one. The other one, oh, I hate drawing this one. It's not a cat. Oh, sorry. I know, it feels like Pictionary. Is it a castle? No, it's not a castle. Yeah.
There's a line on there that looks curved. Is that all one line?
So let me... I'm going to put dots where all of the carbon centers are.
Okay, that looks.
This is a bicyclic ring system where boron is one of the bridgeheads, right? So this boron up here is fusing the rings together. Make sense? All right. So this has a really elegant name. It's 9-bora bicyclo bracket 3.3.1 nonane. So 9-bora bicyclo 331 nonane. Doesn't flow off the tongue super well. So instead, people will call this 9-BBN. 9-BBN is way easier to write out. Yeah. So these reagents are too bulky to react more than once. They'll only react with alkynes. So let's make a note of that. Meaning it's a lot easier to control these reactions. Sorry. All right, I think that's where we're going to stop today. Monday when we come in, we'll learn about that tautomerization where we go from the enol to the aldehyde. A lot of it's just basic arrow pushing though, so nothing too crazy. All right, I'll see some of you tomorrow at the review sessions. If you have any questions, please come prepared with questions at the review session. It'll be at 2:30.